Assalamualaikum warahmatullahi wabarakatuh, and a very good morning to all the students. So we meet again in DRM 1413 Manufacturing Technology. So this is actually a new topic, which is chapter 6. Chapter 6, machining process and tools. So let's look at what are the content for today. Oh, so before that, I would like to see there are several processes that we are going to cover in today's topic, which is like turning, drilling, peripheral milling, and face milling. So these are the illustration for each types of these processes, which we are going to be, which we are going to learn in today's lecture. So this is turning using lathe machine. This is how it is being conducted. This is the cutting tool, and this one is the workpiece, or they call it as a work for short term in this content. And number 2 is face milling. This is the workpiece or work, and this is the milling cutter, and it cut the surface of the workpiece. And then milling cutting. And milling cutting, this one is used to make a hole on the workpiece. And this is the cutting tools. This one is cutting tool. Meanwhile, this one is the workpiece. So for today, things that we are going to learn is the a little bit introduction on machining process, the material removal process, the advantages as well as disadvantages of machining process. And then we are going to look at on the cutting mechanics of cutting, the cutting tools itself, the cutting condition, chip formation. And last but not least is we are going to look at on other parameters involved for machining or cutting, which are force, power, as well as temperature. So again, in this topic, we are going to look at on turning, drilling, milling, as well as grinding. So all these process actually falls under material removal processes. It's either using conventional machining or abrasive processes. And the most important part in machining process is the cutting speed as well as feed. So these two terminology we are going to look at in the next section. The advantages of machining is that it can be conducted to various types of materials or workpiece. It can be used to shape various types of geometries and shape, high dimensional accuracy, as well as good surface finishes. Meanwhile, the advantages for machining is it will produce wasteful of materials and also time consuming, depending on types of and depending on the geometry of our final product. Again, these are the types of machining process that we are going to look at, which includes turning, drilling, peripheral milling, as well as face milling. So these are actually falls under mechanics of cutting. And if you look at this figure, this one for A and B, B is mainly for cutting tool. You can look at this one is the rig, and this one is flank. So if you refer to figure A, you can see the terminology for the cutting tool. Cutting tool itself in general has to be made from materials which is harder than the workpiece or work part. And other terminology for cutting tool includes rake face. This is the rake face. A rake is actually the cutting face relative to the work part or work piece. So this is the rake, and it has a rake angle over here, And flank, this is the flank, this the other surface of the cutting tool, which is relative to the other part of work, piece of work part. And it provides clearance between tools and the new surface. Cutting tool can be divided into two, which are single point tool, like in figure 1, and multiple cutting edge tool, like figure B. So single point tool actually has, why they call it as a single point tool, because it only has one cutting edge, which is 2 point. At this point, from this figure, you can see this is the 2 point, which is the area of cutting. And 2 point is rounded in a certain radius, which is called nose radius. Nose radius. And this cutting tool is suitable to be used for turning a process. Meanwhile, for multiple cutting edge tool, it has more than one cutting edges, as can be seen from this figure. It can be achieve relative motion by rotation, of course, and this one normally being used to make a hole through drilling as well as milling process. In cutting, in mechanics of cutting, like I mentioned earlier, the most important part is cutting speed as well as feed, which is F. Other than that, depth of cut. So the things that we are going to calculate in mechanics of cutting is the material removal rate using this formula given. Material removal rate, RMR, or sometimes they use as MRR, as it's as for the terminology. And for turning, normally it is used to produce a cylindrical shape, and its speed motion actually represent the rotating work part. This is the workpiece. So speed motion is actually referring to the workpiece speed. Feed motion refers to cutting tool. This is a cutting tool. So how deep the cutting tool goes into the workpiece. So that is called as feed motion. Whereas for drilling, this one, as mentioned to you just now, it is used to make a hole, a round hole. Speed motion actually refers to rotating tools. This is the tool. And a feed motion also refers to the tool. So in drilling, the workpiece will not moving. Meanwhile, for turning, workpiece will moving, and cutting tools will stay that way, but it can move. We can move a little bit to determine its depth, to achieve depth of cut. For milling, it can be divided into two: peripheral milling and face milling. Speed motion refers to rotating milling cutter. This one is either for peripheral or face milling. Feed motion refers to workpiece. So in this process, the workpiece will be moving as well to achieve its certain depth of cut. Basic forms of milling: peripheral and face milling. Um, As for the cutting condition, other cutting conditions that in summary, um, um, in machining operation, it includes roughing and finishing. However, cutting speed for roughing is actually lower than finishing. Meanwhile, for other mechanics of cuttings like feed and depth of cut, roughing is actually higher as compared to finishing, because in finishing we don't want it to be high in depth of cut or high in scratches. Other than that, normally, the cutting itself, it will not only be conducted in straight line or in linear. That's also cutting operation which is being conducted in orthogonal direction. So in this area, in this process, you may found the terminology for right angle alpha. This one, okay. It determines the direction that the chip flows. clearance angle. It provides a small clearance between the tool flank and newly generated workpiece. So at this part, this is the clearance angle. So that what happen. That what happened in orthogonal cutting. Um, the other terms or terminology that we need to know is the chip thickness ratio with the formula of R equals to T naught over TC. T naught is the initial thickness of the chip, and then TC is the thickness after it become chip or after it is being cut. Chip ratio will always be less than 1.0. Other than that, we also need to know the formula for shear plane angle, this one, as well as shear strain in metal cutting. So I think let's look at the example in this slide. Let's read it together. In a machining operation that approximates orthogonal cutting, the cutting tool has a rig angle equals to 10 degree. The chip thickness before the cut T naught equals to 0.5 mm and the chip thickness after the cut TC equals to 1.125 mm. Calculate the shear plane angle and the shear strain in the operation. So first of all that you need to do is you need to calculate the value of R. Okay, so R equals to 0.5 initial thickness divided by R TC, which is thickness after the operation, 1.125 mm. So R equals to 0.4. And remember again, the ratio for R must be always less than 1.0. After that, we need to calculate the shear plane angle, and this is the formula. So just substitute the information given in this equation, in this question, into the equation, which finally you will get the value for shear plane angle equals to 25.4 degree. Meanwhile, for shear strain can be obtained from this equation. So again, substitute all the information given in this question as well as from your calculation into the formula. Then you should be able to get the value of shear strain, which is equals to 2.386. As for chip formation in metal machining can be divided into 4 types. Number 1, discontinuous chip, which can be seen in figure A. So this is actually discontinuous chip, whereby it is being produced when brittle material is machined at low cutting speed. It will produce irregular texture, high tool chip friction, and large feed and depth of cut also promote the formation of discontinuous chip. Number 2 is continuous chip, which can be seen from figure B. It occur when ductile materials are cut at high speeds with relatively small feeds and depths. Will result in good surface finish, sharp cutting edge, low tool chip friction encourage the formation of continuous chip. However, long continuous chip can cause problems, and that's why for these types of chip, we need to have a breaker. Number 3 is BUE, or a build-up edge, BUE. So it occurs when machining ductile materials at low to medium cutting speed. So this is build-up edge. BUE consists of layer of material from the workpiece that are gradually deposited on the tool. BUE then becomes unstable and eventually breaks up. BUE material is carried away on tool side of the chip. The rest is deposited randomly on the workpiece area. So these are the particles of BUE on the surface. BUE can reduce the life of cutting tool and results in poor surface finish. And BUE can be reduced by decreasing depth of cut, increasing rig angle, use sharp tools, and use effective cutting fluid. So again, this is BUE, location of BUE. This is what will happen when particle of BUE distributed on the surface. So that's why the surface will be smooth. Instead, it will become much more rougher. Number 4 is serrated chips, which can be seen from this figure. It occurs when the difficult to machine metals such as like titanium alloy, nickel-based superalloy, austenitic stainless steel are machined at higher cutting speeds. It also happens when common metals are cut at high speeds. So this is how the location for chip breaker being placed at the cutting tools and the workpiece. So this is the chip breaker, and its function is to remove the long continuous chip, because long continuous chip is undesirable. We don't want it because it will entangle and um, will make the process much more difficult. So that's why we need chip breaker to cut that chip before it become long and continuous. Um, there are also various chip can be produced in turning, which is, for example, number 1, tightly curled chip. So this is the illustration for it. And a B, chip hits workpiece and break. Okay, it can be formed that way as well. C, continuous chip moving away from the workpiece. So you will see the circular shape. And D, chip hits tool shank and breaks off. This also can be happen. And other than that, in this process, in machining process, the parameters that we need to know, we need to consider is its cutting force, power, and temperature. Cutting force that we need to consider in this process is forces acting on the chip, this side, and forces acting on the tool, this side. And the rest are the terminology that you can look at on your own. Like F is the symbol for friction, and a symbol for normal force to friction. A formula for friction. This is a formula for coefficient of friction between tool and chip equals to mu equals to F over N. And the angle, so you can look at the terminology for this one. Same goes to shear stress. This is the formula for shear stress. And A, area of shear plane. So this is the formula for a shear plane area before you want to calculate the value of shear stress. And FC, cutting force, FT, cutting thrust. So you can look at all the terminology again over here. Other than that, power or specific energy required to cut the materials is actually different when different types of materials being used. So every single time you want to cut the materials, or what you want to machine the materials, you have to refer the specification for each types of the materials, and you need to set the machine according to its specific energy or power. This one is the temperature distribution at the cutting zone. So if you look at this one, this is the cutting tool. This one is chip. This one is a workpiece. So if you look at this one, the temperature, a higher temperature exists at cutting tool. So for example, this one 500 degree, 600 degree, and this one 650 degree, and so on and so forth. Number 2, followed by chip. If you look at this one, the temperature for chip exists is 360 degrees C, 380, 360, 400, and so on and so forth. As compared to workpiece area, the temperature is much more lower compared to the rest of other components. So I think that will be all for today's lecture. And for next class, we are going to continue in chapter 4, which is new subtopic, which is actually on the cutting tool. So see you again in the next class. Thank you very much for your kind attention and time, and see you again. Had fun. Bye bye.